And welcome everyone to today's Synergist webinar, Calibrating 4,500 Air Monitors in 60 Days. I'm Ed Rutkowski, editor of the Synergist, a magazine of AIHA. I'd like to thank everyone for joining us today, and especially SGS Carlson for sponsoring this webinar. Today's speaker is Ron Mcmahon, Director of Business and Solution Development at SGS Carlson. Ron's background in advanced systems from robotics, instrumentation, sensors, communications, and cloud-based platforms provides SGS the insight to develop leading-edge offerings to simplify, automate, or enhance the way EHS functions are performed for SGS clients. His background as an expert in the environmental field increases the importance of accurate, defensible data and understanding of the requirements of lab or real-time devices to provide the best options for valid data. Ron's industrial engineering degree from Texas Tech is the fundamental for reducing related cost and time using automation. Now I'll turn the presentation over to Ron.
Hey, thanks, Ed. Great, and welcome everyone. I see some friends have joined. That's always good. Always good to see all the old AIHA friends out there. So this is going to be an interesting talk. I hope everyone contributes to this. This is, I think for everyone, this is a learning curve. Having this many air monitors and basically one situation or one system and trying to maintain 4,500 air monitors and calibrate them is a monumental task. And it has been a very interesting experience. And so just to give you some background, last year, SGS Carlson was awarded a contract, SGS North America, for installing approximately 5,000 air monitors into Boston Public Schools, as well as putting our outdoor units on top of every building roof system so that we could monitor the outdoor air as well for comparative reasons. And so everyone knows that we don't provide field services, we don't do those kind of things, but we did, in this case, act as the project managers, and we partnered with TRC to do the installation. Installation took us just over 2.5 months, 3 months. And during the initial installation, there were calibration checks, things were done as we went. There were teams of 10 to 12 people doing installation. And overall, it was pretty amazing that we got it done in the time frame we did, trying to get it done before school started. So it started around the 1st of July and ended up in September. And then some of the roof units followed in October. So all this data is sent to basically a web-based platform. And then is presented not only on a public website, but we also have a technical back end that ourselves in Boston Public Schools uses to monitor the status of the sensors and any sort of failures that might be taking place. So this talk today is lessons learned about that, and also just overall how, in my opinion, how we see things moving forward, and that your old typical indoor quality solution set or how people thought about indoor quality is changing. And I'm going to show you some things that will maybe generate some thoughts on your end, but the biggest thing is the engagement. We see a lot of industrial hygienists not engaging in this because of low-cost sensors and different things, and yet we see a need to really start for IHs to take the lead on this, and I'll explain why as we go forward. Just a real quick, I want to shout out some recognition. Boston Public Schools is just a great client. They're easy to get along with, very supportive, and you can imagine trying to get into 123 buildings at any given moment. Trying to do what we do was monumental, and they have a right approach, and they're very, very long-term oriented. They see this going on forever. This isn't a Band-Aid. This is an application that's going to work for a very long time. TRC and their efforts were very appreciated, especially Heath Howard and his ability to put together a Fulcrum program that allowed us to do the documentation needed to be able to place these sensors in the right classrooms, to track calibrations, to track accuracies, all these things really helped us. And Atlas is now part of our team, ATC Atlas, to help maintain this system and provide according response when we do have a problem with any of the units. And then obviously the Galton team, SGS Carlson, Chris Shepkop, and everybody back at the East Syracuse lab was what an incredible effort. So good work, everyone. It was awesome, and here we are. And We're now into the just the completion of the first year of calibration, which is part of a multi-year contract included in what we do. So it's not just install units, walk away. There is actual plans of maintaining, keeping them, calibrated, and maintaining these instruments as we go forward for years to come. So let's get into the meat of this. Thanks for attending, everyone, by the way. So we're just going to go, first thing is to talk about how what's happened really due to COVID and how people are viewing indoor air. You know, the way we viewed CO2 readings, the way we viewed particle measurements, things are changing because of what's occurred with COVID. And we'll get into some of that. CIH is needed. Everything that's going on with regards to indoor air quality now is really becoming an exposure risk. And so CO2 may not in and of itself be an issue until much higher concentrations, but based on air exchange rates, based on things that are going on to help reduce risk of spread of infectious disease and different things is really taken hold. So there is legislation, there are a lot of things going on right now that are pushing hard toward trying to monitor two key elements, which is filtration and ventilation. And I'll get into that in just a second, explain that correlation. We'll then go over the calibration process that we use. This is the real meal deal. All of you have calibrated instruments, I'm sure, but to calibrate 4,500 in a very short period of time is interesting. And again, with the right automation devices, with the right software programs, it becomes something that's manageable. But when you start getting down to the last couple of units or few units that you got to deal with, it's interesting. All these units communicate either by Wi-Fi or cellular, and they hit the cloud. And again, there's things like connection loss because of Wi-Fi outages or power disconnects of power or whatever. So all these things come into play to try and achieve these goals. And then the one thing I think is really interesting is the sum of impact of calibration accuracy. These things are going to be challenged. We're being challenged. We've got some of the universities involved with us now with BPS, and the data will be challenged. So CIHs are the solution to providing the best data and being able to meet these challenges. And I think it's really important that we see what can happen to the sum of the inaccuracies and uncertainty, which is exactly the term used by our own lab people in AIHA for accreditation, the uncertainty of measurement and how all these things could be impacted in what we could be facing as we go forward in these challenges, and understanding just how stacked up error can just be incredibly huge. And everybody really needs to understand that as these challenges do come forward. So IAQ in buildings it's not just the old simple thing anymore. This is now moving toward an exposure risk. We all know that CO2 levels or filtration, ventilation, in and of itself don't stop the spread of infectious disease. We know that. But through COVID, it's become apparent that this is something that increases the risk factor. So now we're talking about measuring things and taking action and doing things to try and reduce exposure. Now I'm familiar, that's what industrial hygienists do. And now with everything going on around this, I really think we have to start to treat it like that and apply the same principles, the same IH rules that we've always applied to everything we do. Just in this case, now we're moving into something that the volume and the number of people looking at this data, round numbers so you get an idea, 50,000 students, 100,000 parents, 300,000 relatives, 50,000 teachers, administration. I mean, everyone wants to know now. And the question will be, how is that working? Is it accurate? Does it work right? How do I know about the data? How do I know the data is good? And just what is that extrapolation now between, well, if we're at 1,000, what does that mean? CO2, or we're 2,000, what does that mean? So it's no longer look at the permissible exposure level for CO2. It's what could be the implied added risk if we don't have proper ventilation. So these things are all starting to happen. So the first one obviously is filtration. Particle measurement can do a lot of this. There are a lot of older buildings in the world that do not have mechanical ventilation. Things going on to try and filter the air. So it's just, it's critical that we move forward with this, and that we understand filtration is a primary component. The White House has come out, EPA, CDC, everything about filtration and ventilation. Again, ventilation, super important. We all have used CO2 in the past, direct indicator of proper ventilation in a room based on occupancy. Some buildings don't do anything with controlled ventilation. Some do. Some of the side benefits of installing this number of units in buildings that do not have mechanical ventilation or have not installed CO2 sensors. Now with cloud capabilities, we can push this data to building management systems and even impact that directly, as well as being able to provide just local outputs to turn on something, a fan or whatever, to start circulation of the air. Obviously, we now are looking at, we can look at other things, low-level carbon monoxide exposure, something that's been talked about. If you're going to install an instrument that's got some of these primary features, temperature, humidity, carbon dioxide, and particles, what else can we add to it since the platform is there? So a lot of people stay away from low-level carbon monoxide. They don't want to know about carbon monoxide. This is one that, is something that can be, if it's not done properly, there could be problems with protecting occupants. So a lot of people shy away from this. But if you're using a proper product, you're using a proper sensor, and based on the number of sensors in the schools or in a facility, there's a lot of things that provide redundancy. So it's all very, very safe, and it's a good idea because we've already found multiple things that are causing low-level CO exposures in different buildings, and people can take action to resolve that. Just like the IH standard, you try to engineer it out, trying to eliminate the hazard. Same thing. If you know about it, you can deal with it. If you don't, you won't. So we're talking about being able to respond down to levels in the 4 to 5 ppm range, using an electrochemical sensor just like what you have in all your confined space monitors. Same technology made by AlphaSense, so very reliable. VOCs, there's a lot of what I call metal oxide junk VOC sensors on the market. There's some that work okay, but there's still no correlation to action level or what it's really detecting. And there's a lot of cross interferences as far as environmental influences. But again, it's something to look at. I know Ion Science is now releasing a low-level, lower-cost PID for indoor air quality. We're in the middle of looking at this and trying to get the cost down for PIDs to go into these type of instruments so that you can have an effective VOC sensor, not formaldehyde, but for other VOCs. Again, temperature and humidity. Again, these are becoming even more critical. I saw something from Michelle Rosales. I'm calling you out. Forensic Analytical Consulting, talking about some of the legislation coming out with regards to temperature exposure. It's starting as low as 80 degrees for workers. Well, from an indoor air quality standpoint, same thing. Temperature and humidity, not only are they comfort related, but there's more impact that's being determined that should be monitored and action be taken. So more of these things are going to become, I think, more and more regulated as we move forward, and the indoor air quality becomes a more critical factor. So when I say CIHs are needed, I really mean it. Back in the day when mold got going, the AIHA and the ACGH tried to make it so that if you did a mold survey or you did something around mold studies, you would have a CIH sign off on it. And it became a very common event that CIHs would sign off on, any plant or to remediate or abate what's going on. I really think that we're in a position now with CIHs that they should be a part of the indoor quality program. A lot of CIHs already do indoor quality studies. They do all these things, but it's so critical to install them correctly, manage them correctly, plan things out correctly, calibrate correctly, validate calibration. It's not as simple as sticking something on the wall and it works. There are just a lot of manufacturers that have fixed parameters for zero and span. They do auto cals, they do all these things that will be challenged because there's the span and the drift of these sensors are being compensated for, and it may not be exactly what needs to be done. So without treating it like a true instrument, there's going to be some issues, and we can see them coming, and we already see some of these challenges. So the key for CIH is, as you all know, in industrial hygiene is what do we do to have defensible data, accurate data? When people go, hey, how do you know this works? It's the whole list of things that an expert would answer the question, hey, when did you last calibrate it? Give me proof of calibration. What quality did you use to calibrate? What accuracy were all these things that you used to calibrate? You know, one of the big things is elimination of false alarms. A lot of people don't want to see false alarms, but when they do that, they impact potentially not seeing alarms when you should see alarms. When I say alarm, I'm talking about like notification of 4 to 5 ppm of CO, 800 ppm or 1,000 or 1,200 ppm of CO2, high temperature, high humidity, whatever it is. But when these things start occurring, if it's not calibrated properly, and companies do things in the cloud or in their own software on their firmware to sort of hide that or auto-correct it, it could be the other way. You could actually be missing some of these issues that don't come forward because they're being hid by some methodology, some algorithm. And so it's just super critical that when, just like everybody on this phone, when you calibrate an indoor quality meter or a particular instrument, you got to know it's right. And you do that through showing it test gas. You do it through reference instruments next to you, on and documenting that. And so I just think it's going to be so critical. These things become commonplace when you start putting these numbers of indoor quality units into these buildings. And then the last piece, obviously, is cost effectiveness. One of the advantages, and this is, okay, I'm going to plug SGS a bit. We have the ability of doing lab analysis. So, hey, if you want to do a PM, we're going to send you a pre-weighed filter. Here's the cost, $50. Boom. No, I want continuous. No, I want to use a handheld. Our capability to provide any of the solution sets to make it cost effective and make it the proper solution all sits within one house of SGS. So when a client needs something, whether it's analytical, whether it's real time, whether it's continuous, whether it's cloud-based, all those things we have the capability of providing. So we're not trying to provide you something that we have. We're trying to provide you what you really need for your situation. So let's talk about the calibration. So I'm just going to show you a simple just diagram of this. If anybody would like to see what these look like, whatever, we're glad to take you through a demo of everything that we've got. But basically, it's an air monitor. We use certified test gas. We had Fulcrum loaded on all the technicians' phones. It was done by TRC and Heath Howard. And so very clever. Number one is when we did this round coming back in this year, it sounds very simple, but 4,500 units. Is that unit still in this classroom? Is it the unit that we initially installed in the classroom? So the first thing was by scanning with Fulcrum the barcode, it pulls up the record of installation and says, hey, you're in room 307 in this school, and yeah, that's the right unit. So right away, the first thing is confirmation that this instrument is the instrument that was placed in this room. The second thing then was to record with reference instruments in the room with you, and I'll show you those reference instruments in a minute. What were the readings on the reference instruments? Now, what's so critical and what you learn by doing 4,500 of these and having all these different technicians is don't breathe near the equipment. Don't be by the equipment. Don't do anything to create any variance that's not the real atmosphere you're in. So we determined very early that we had some people that would use the instruments and they would be too close to the CO2 sensor or whatever, and it would cause this variation. And so those kind of things come into play. And so number one, are your reference instruments working properly? Are they calibrated? Number two, use them effectively so that you don't cause an interference or any inaccuracy whenever you're recording these when you start to do the comparison and do the calibration. We would then record the readings of the reference instrument. Again, after you've scanned the barcode, you're able to go document the readings right now before I do anything. And now you can compare those readings to your reference instruments. They're all in one place in Fulcrum. The next step is now to apply the gas. So we had the ability in this chamber, basically, it's got its own little chamber. We cover the chamber, apply the gas. We've tested what flow rates need to be done. And we know what the output of the sensors look like because we look at the actual output of the sensor without calibration. So we know if they're in range or not. So we apply the gas, and now we allow it to stabilize 6 to 12 minutes. We did not use zero air because it would extend the calibration to over 30 minutes. We used the reference devices to set the 2-point calibration for CO and CO2. So then when we applied the gas, it was 5 ppm of CO, 1,000 ppm of CO2. The unit would stabilize in 6 to 12 minutes. Once the technician would see the reading stabilize, because he can see the instruments reading through his app by connecting to the cloud, he would go, okay, good, I see it. And now we recorded what the response was on the instrument without any calibration yet. So what was the instrument reading when we got to the room? We applied the 1,000 and the 5 ppm respectively. What did it read? And we recorded that so we could look at what the accuracy was of this instrument basically during the last year. Again, there may be some drift or some small changes, but in indoor environments, typically you don't have very aggressive sensor drift or changes. And so it's very useful to be able to compare that data now to where we were. So, and in the process with the university in Boston, we're working with them to actually be able to back calculate that and provide 2 data sets. One that says, here's what it was, and one that says, here's the corrected data based on our latest calibration. So again, and both those will be public. Both of them will be available. And we have a lot of research teams looking at this data, so we're trying to nail it down to make it as accurate as possible so that all the greatness of having this information and whatever people can come up with to improve the environment with this data, it's accurate and it's meaningful. So then, our partner EchoMeasure, our hardware partner and our software partner Terabase on the platform, EchoMeasure did a great job. They're our hardware partner and they're the first initial touch for the actual web connection. Through the year, we had very little drop in connectivity due to anything to do with the servers. 4,500 units. I think we looked at maybe an hour and a half that we actually were interrupted due to server issues, which is so minute compared to a terabyte of data we were accumulating every month. So in the automation of calibration, it was really clever. EchoMeasure put together this program, and it all is displayed on your phone or on a tablet or on a computer, and you literally can see the trend of what's going on when you're calibrating, and you're able to set your 0 or your first point, your second point, and then make the adjustment. And on any of the reference devices, you're able to enter the reference and again select where that is and then make the adjustment. And super clever. Even what was really clever about the whole calibration piece is if you needed to calibrate or look at what happened, you can pull that calibration record down, and knowing when the gas was exposed to the unit, you can actually go back and look and see if there's any correction needed. So you literally can work off of the exposure or the sampling period to make any adjustments if it's required. And it was just really cool. And so anyway, all those things took place. That was the mode and the method of what we did. Again, I look forward to sharing this with anybody that has the interest. So this is what we were talking about. The 0 error extended time using nitrogen or background against the reference level. So we did not use 0 error nitrogen. We did use reference levels using it, and I'll show you the instrument. It's a TSI, and then we use certified test gas from Portagas, or they've been acquired now, but that was the test gas that we used, and we had the combination of CO and CO2 in a single bottle, so it made it very simple to use. Then PM 2.5, again, we had reference estimates. We used the arrow set. We would every other day, every day, we would take the arrow sets, line them up before the technician started, make sure they were all within range of each other as our QA. And then those units, we had units that had just been delivered that were certified, arrow set MET 1, and then we would use that as our reference as we went into the field, and they would for 2.5 and 10. And so you would use that to go in, and that would be one of your reference measurements you would take. And the TSI actually was also used for the temperature and humidity and low-level CO. VOCs, we didn't have any VOCs in this case, but it very easily could have done. We could have done the VOCs if we had them. But again, we're a favor of PID technology in this application, not the VOC metal oxide sensors, because we don't know what it means. We don't know what the correlation is. There is no data like on a PID of how to check, based on isobutylene, what's the concentration if we have this. So again, with the new low-cost PIDs coming out from Ion Science, we hope we can engage with that and provide a solution that makes some sense. Formaldehyde sensors, again, there's no way to calibrate them effectively. You use a surrogate like H2S to calibrate those. And this is an area where we think it's better just to use a badge. Use an analytical method. It's inexpensive. It's much more accurate. It's everything to do with specificity and low-level detection that you need for true formaldehyde detection. Again, that's not to say that there's not some good sensors coming. There's some that may be okay now, but we just don't see those working effectively at the levels they need to work with no cross sensitivity. Radon's another one we're adding to this. We don't have it now, but we're working with a company on a radon device that is certified, and it's reasonable and it's real time and can be added to the cloud. Keep in mind that our cloud is agnostic, either EchoMazur or Terabase, our partner for LiveView. We can add any sensor in. We've even got real-time GCs that are connected to these, and we'll be moving forward with more of that type of technology to advance things. Again, temperature, humidity, same thing. It's a matter of having reference devices and checking that and making those corrections. And it was very effective. And so the next thing that I think is so interesting is when you go through a calibration process like this and you're looking for the uncertainty, measurement uncertainty, that's the key. And you have to do everything you can to eliminate anything that can cause uncertainty in your method. And using the right test gas, the right things, the right instruments, the right calibrations, on and on and on process. So I want to show you something that is, to me, why CIHs need to be involved and what you need to be looking for or looking at when it comes to the data that's in these instruments. In our case, or anybody that's putting these devices in, what if somebody comes and challenges it? What could be the variation? And sometimes we don't think about it in this way, and I think it's super important. So the first thing to note, and I'm going to go through these a little bit quickly, but the first thing is uncertainty. Well, the first thing is test gas. Test gas right on the bottle state 5% to 20% plus or minus, depending on the test gas. So if you just go, hey, let's look at 5 to 20%, then on 1,000 ppm of CO2, it could be 950 to 1,050, or it could be 800 to 1,200, just based on the test gas, and anything in between, right? But for purpose of exposing this whole thing, let's assume the worst case. Okay, the Aeroset and the TSI, they publish their accuracies. What's their accuracy? Again, plus or minus 5%, plus or minus 20%. So using a reference device that's calibrated with the test gas we just looked at, what's the inaccuracy? What's the true uncertainty of this measurement? And again, it could be 5 to 20%. So these are right out of the manufacturer's book, and it's plus or minus 3%. The PM is plus or minus 10%. We had 2 or 3 different manufacturers of PM sensors, and the variation, even though they said they were all calibrated to Arizona road dust standards, all these things, the variation was unbelievable. We trusted the Aeroset, and we stayed with the Aeroset because of its repeatability between all the instruments. And so at any moment, we had 8 to 10 Aerosets in a building or with the technicians, and we trusted the measurement. But again, even it's plus or minus 10%. Human element, like just people being doing things incorrectly in the calibration or the standard, or somebody had been in the room and they're no longer there, all these different things. What could that introduce? Could someone have excelled close to the reference instrument or excelled on the smart sense unit on the wall to have caused variation? Again, what if it was around 5 to 20% plus or minus? So then the CO2 sensor itself, what's the accuracy of the CO2 sensor itself? And temperature compensation, is it done properly? This is the specification directly from the manufacturer. So plus or minus 10 ppm, 0 repeatability, full scale, plus or minus 50 ppm. So just full scale, plus or minus 50 ppm on a 0 to 2000 ppm sensor. I mean, it's 50 ppm. That's, there you go. So we're getting into more stacked error. And again, we're trying to do everything we can to eliminate the uncertainty. So keep in mind, the key here is somebody's going to come in, walk in with some device they got from somewhere, and they're going to go, hey, how come mine's reading this and yours is reading that? And all of these things come into play. Every single one of these come into play. The effect of temperature and relative humidity on a device, the CO2 sensor, for example. The application of your calibration process, whether it's the product on the wall or it's one that's in the handheld that somebody's carrying or whatever. So all of a sudden you go, okay, let's take the worst case. The person that walks in with a test device has the very low end, and our device is the very other end, right? And we do everything we can to bring that down into the 5 to 10% range accumulatively. But what if it's completely on opposite ends? You literally could be off from 1,000 ppm. It could be anywhere from 500 to 2,500 with a cumulative uncertainty. And again, I'm exaggerating it, but this is how people could get to a point where they're going, hey, why are you reading 1,000? I'm reading 2,000, right? And so it's like, well, can you give me some information about your device? What did you do? And how did you calibrate it? When's the last calibration? What's the effective temperature meaning? On and on and on. So how do we document things on our end as industrial hygienists? What do we do to document all this? So this is our documentation file for every single compound that we calibrated, or with or without a reference, or with test gas. So we literally have the data showing before the calibration. Remember, we stored that data. And then we show the data after calibration. So this is CO2. So this instrument, when we got to this instrument on the 1,000 ppm, it was reading 1,200. So it was just above 20% inaccurate, reading high. When we got done and we put in our reference value, right? And you can see that the other one was reading high as a reference. When we got done, it was only 425 as your first point, and your calibration point was 1,000. And the line shows you, the green line shows exactly what it did. And we do this for every single sensor in every single instrument, all 4,500. So this is the kind of documentation as industrial hygienist. Somebody goes, hey, and already talking to BPS, sometimes it's like, if somebody challenges a sensor, we're going to mail them the calibration file. This is where it's headed. This is where people have got to be able to look at the data and know that it's been done by a standard or an industry standard that can hold up to the challenges. And IH is understanding where the challenges come from, how the inaccuracies can occur. We all live through that. And again, the sensor committee at AIHA, that was a big concern. Somebody walking into an industrial setting, looking at their watch going, hey, I've got 10 million ppm VOCs, and why are you showing 5? And, AIHA was very concerned about that, and I'm not sure where that program is, but it's the whole idea of having sensors that are calibrated and working properly. Are they really working properly? How do you prove they're working properly? And this kind of documentation and calibration is the only way. And the people that know how to do this with regards to exposure are CIHs. That's why the whole industry of industrial hygienists, AIHA, needs to get behind, in my opinion, leading this march. Almost to the point where the specification in a city or a state or whatever, when they start to develop this legislation, says this program needs to be verified, inspected, and maintained and signed off with a program done by a certified industrial hygienist, because that's what we do. That's what IHs do. And nobody else does that when it comes to exposure. That's our job. So I really think that instead of not engaging, maybe because it's a low cost, it's all the people, there's a lot of, moms and dads and different things, I think it's exactly the opposite of not engaging. I think we have to engage, because otherwise cities and states and our federal government will spend a fortune on product that in 2 years will be no longer looked at. No one will care. Nobody will have trust in the data. And trust me, there will be people challenging this data well above just going, hey, I don't think you're reading right? It's going to go to a higher level. And I think that's not far away. And we at Galson, yes, we have to do exactly and make this the best we can. And every day we're improving. And a lot of you have used our product in certain applications, and it's getting better and better and better. And we continue to improve it. And the key is to make sure the claims make sense, that the claims are understandable and people believe in them, or else it will be useless. It'll be useless and it'll go away. Boston Public Schools is doing it right. It's part of the contract. It's up to us, and we have to help them get there. And it's just a full-time thing, and it's an excellent program, and I applaud them for what they've taken on, and they're out in front of it, and they got the right attitude to do it. So this is an interesting curve. This is our after calibration. And so 4,300 instruments, whatever the number is at this point when we did it, the line that you see, this is all sorted. The after calibration reading, that was documented. And all I did was take it from high to low on CO2 and CO. So you can see that the 1,000 ppm of CO2, the majority of the line is right on. But you can see the outliers that we have to take care of that create some of the error. But the amount of these units and how accurate they are is incredible after calibration, right? And even before calibration, a lot of the readings we didn't know where it would end up, and so that's another story to tell, is what was the accuracy prior to calibration. And then you can see CO. Same thing, right along that 5 ppm, but you can see the outliers that we have to investigate. What happened there? Was it a calibration issue? Was it a technician issue? Was it, whatever? Was the sensor not reading properly? Is the sensor bad? We've had about 50 CO2 sensors stop reading. Some of that occurs in this, and it helps you figure out what's going on, and you keep troubleshooting it. You don't ever stop troubleshooting it because it needs to be done continuously. Or else, again, the program won't work. It just won't work. So the sum of the impact of measurement uncertainty. Here's just an example. You probably recognize where this came from. But there's a $42 unit that reads everything out of Walmart. There's a $396 wireless unit, CO2. There's a $430 one. There's a $915 one. There's a $52 one. They're all over the map, right? And some of these can be calibrated, some of them can't. Some of them are for explosion-proof environments. Some of them are not. Some are for in-duct measurements. Some aren't. I mean, it's this plethora of things. But at the end of the day, it's CO2 and particle, CO, all these things, VOCs, temperature, humidity, noise, it all has to do with exposure. It's becoming an exposure issue, not, hey, hey, we got a little elevated CO2. Yeah, it's not a problem. It's not 20,000 yet. It's going to get to the point where there is lower concentrations that need to be accurate, that can be trusted, so that people take the right action. They take the right action to take care of it. So these challenges to these kind of companies is, hey, when's your last calibration? Can you give me documentation? Hey, do you have any third-party validation of this unit, the one that I've got in my hand? Not the one you sent to XYZ for study, because we know what we do there. Hey, can you give me the true technical specifications? Let me see what your claims are, because I want to see if your instrument performs to your claims. If it doesn't perform to your claims, then we got a problem, right? If it's not right, then if one's not right, what about all of them? And then the reverse challenge side by side. Hey, the best way, let's go get an AQM 65 air monitoring station. We can put that on our platform. Actually, we can put it up on the platform and do a comparison. But let's do it side by side and see how this thing ends up. So this is great. This came from our QA manager, Denise, and she sent me the uncertainty contributors. And this is what the laboratory, SGS Galson, processes over 350,000 samples a year for industrial hygiene. And this is what we have to go through whenever we go through our renewal of our accreditation. And what it is you go, hey, what's the contributors to uncertainty? And then what are you going to do to control it? What will you do to control that or minimize it? And this is the mindset that we're taking toward real-time measurements as well with continuous platforms. How do we do this? What do we got to do to control all those things that stack up into an error? How do we mitigate that? How do we make sure that we're not creating the error? Are we doing the best we can? So this mindset rings out through all of SGS of being able to control the uncertainty of the measurement. And it's critical. And this is how the mindset has to be. This is how IHs think. And that's why we need to get everyone involved in this and help drive legislation to make sure that we don't waste all the public waste, millions and millions of dollars on these devices that are not going to be what they need to be to provide the data, reliable data that's required. So at the end of the day, maybe IAQ plans and implementation and maintenance and everything should be required to be done by CIHs. They should sign off on the plan. They should be a part of the plan. They should oversee it and make sure for years that it's done properly. Because any one classroom, any one child, one unit, one thing, got to be done right. We can't not do it right. And we know there's going to be errors. We know there's going to be failures. It's got to be maintained and it's got to be ongoing. Got to be, or it won't work right. And then everyone will forget them, and away we go to the next thing. That's it. Thanks, Ed. Thanks, everyone. I hope you found this interesting. And again, any questions, if you want to reach out to me directly by email, whatever, we're glad to talk. We'd love to get involved with all of our clients. Our clients are the best clients in the world, and you're the right people for us to support to bring this to to your area and to your clients. And we're there to support you, and we'll do everything we can to help you. And thank you so much for your time.
Hey, thanks, Ron. It looks like we have about 20 minutes for questions. Just a reminder to our audience, if you'd like to ask a question, please type it into the chat window on the right side of your screen. First question comes from Brian, who asks, as a CIH consultant, do you advise your clients that IAQ measurements represent employee exposures, and as such, employees and occupants are entitled to results?
So we don't consult, right? That's left to the body that we provide the data to. And you know, everything that I said in this seminar really is to point out the fact where we think it's going and why it's so important that CIHs get involved. We're the provider of data that gets interpreted by people like you, Brian, and our clients. We don't interpret the data. In the case of like continuous monitoring, we're given what the parameters are, and we put those into the alert situation, whether it's texting, email, and so that's why it's so important CIHs get involved and make those recommendations and help mitigate whatever's going on to make it a better situation.
Okay, thanks, Ron. This question from Michelle. You might have answered this during the presentation, but if so, I think I missed it. How often were the units calibrated?
So we, in the proposal for the multi-year contract, we put in annual calibration. And so we're just completing that round, these 4,500 units, and working with the university in Boston and BPS, we're looking at all this data, and we think 1 year will be sufficient based on the technology that's in the system. But and it looks solid right now, but it could get to where we maybe do it more frequently. But at this point, it looks pretty reliable. The measurements from the previous year, we had some error, but you know, greater than what we've got now on the calibrated system, but not crazy off, not 100%. So it's if it needs to be increased, we'll work to do that in a time frame better than 1 year.
Okay, thanks. There's a question from Luis who asks, are there any reliable software or applications to document calibration equipment and keep records current?
So our LiveView system has the ability of storing documentations against locations. And so that's one of the things we're moving toward, is to do those kind of things. Some of that involves, we're working on 3D modeling for a facility, so you can actually tag exactly what's going on. You could have a little window to the side that says calibrated instruments, reference instruments, all those kind of things, and you could just keep track of it by taking basically a PDF or any kind of document format and attaching it to the to like a geotag location.
Okay, thanks, Ron. Chris has two questions. I'm going to ask them both right now. What does the calibration adapter look like for the EcoMeasure units? And what is the flow rate used for the calibration gas to the cal adapter?
So the cal adapter, basically it was just tubing to a nipple that goes into the side of the instrument. And then we used different things that would seal the front part of the unit all the way down to where the inlet was to the particle sensor. And the flow rate was 0.4 to 0.5 liters per minute. And if we used more or less, it would potentially take a lot longer and starve out. If there was more, then we would actually see a potential pressurization, and then the readings would be off.
Okay. Another question from Luis having to do with the frequency of calibration. He asks, is it worth calibrating instruments on an annual basis if they're old, say from the 1990s, and outdated?
Okay. Yeah. So, yeah, I would say depending on the sensors. I mean, when you look at sensor technology today, what we use in this instrument, infrared CO2 from AlphaSense, electrochemical AlphaSense, CO sensor, temperature, humidity, the PM sensors. You know, the expected life on these things is, except for PM, you know, could easily be 5 to 10 years and longer. Because we're in an indoor environment and we're not aggressively showing this thing in inordinate environments and high concentrations of gas, typically, you know, we should not see a dramatic shift in output. The one that is interesting is the PM sensor, because there can be an accumulated dust situation that we've seen when we have a classroom where they're stripping the floors or they're doing something and the dust levels go extremely high, that there can be some coating of the optics that could cause the unit not to return back to its zero level. And the other thing is that the flow rate with the fan and PM sensors needs to be consistent. So over time, I think the PM sensors in this case will be the ones that really need to be watched. So if you got a 1990 unit, I mean, probably if they're electrochemical or, you know, I don't know, some of the infrared sensors just keep going. But validation with calibration is the only way to do it, right?
Okay, thanks, Ron. Stephanie asks, you had mentioned that you gassed the equipment using a chamber. How did that compare to using the calibration adapter?
So the unit actually has its own, it's like a built-in chamber in and of itself. So it's literally like creating its own little chamber for the sensors. Typically, that chamber is open through the, if you look at the Smart Sense unit, it's just got a cross on the front. And then it's got, you'll look down to the bottom right and you'll see the inlet for the particle sensor, which also exhausts air into the chamber. So when you block all that off and you put the gas into the chamber, it's literally like its own little mini chamber.
Okay, thanks, Ron. Another question about documentation. How did you document the before and after results?
Yeah, so again, I got to give it to Heath Howard at TRC. He's really a database expert, especially utilizing Fulcrum. And so it was all automated on the app. So when you scan the barcode on the unit, you would identify that it's in the right location. The first thing you would do is then put in your reference levels into that record off your reference instruments. And then you would hit a single button, and by hitting that button, it would connect to our platform and actually go to that serial number and pull that instrument's information down right into Fulcrum. So then you would do the same thing when you exposed it to gas prior to any calibration adjustment. It would do the same thing. You would say, okay, it's stable. Okay, give me the readings now. And now when the 1,000 ppm and 5 ppm were applied, it would pull out those readings out of the cloud and again put them into Fulcrum. And then once you did your calibration, you would wait until the readings would adjust accordingly, and you could just see it move. You would see the CO or the CO2 readings adjust, and then when it stabilized, again through Fulcrum, you would hit the button again. It would go to the cloud and download those readings. So it was all automated. There was no, other than the manual entry of reference instrument numbers, everything was automatically delivered to Fulcrum through the cloud, through the program.
Okay, thanks, Ron. Next question, did the school include the calibration in the contract?
They did. They did. Well, and yeah, exactly. And so it was an annual calibration for the term of the contract. Yeah. So this will be our first year that we've done the field calibration, just calibration, no installation.
Okay.
I think that's critical, by the way, just my own opinion. It makes things more expensive, but we all know if you're going to do it right, a lot of times it's just going to cost more. And I think that's a function that's so critical for documentation of accuracy and what the instruments are reading.
Okay. Next question is from Susan. She says, I'm all for CIHs having a major role in IAQ, but I understand in my state, California, that attempts to mandate CIH roles in general are viewed by regulators as, quote, self-serving. Do you have any thoughts on that?
Yeah. Yeah. Well, I think that's been going on forever. That comment goes on forever. But the reality is, I mean, in this situation, there's a lot in this. I mean, all the way from where to place it, and schools are all different. I mean, it's crazy when you start installing these units. But at the end of the day, if a school is going to go, okay, I'm putting the board of directors, school board is going to go, we're going to go do this. In my opinion, they're not going to do something that they can't stand behind. So if they go buy an $85 instrument and put it on a wall and expect it to be okay, especially in California, the litigation around that could just be enormous. And I think from a risk standpoint, liability standpoint, I don't think people can afford to do that. And as a result of that, I think legislators should be looking at it, thinking the same way, that, man, we need to make sure this is done right, because this could be, it could be bizarre. I mean, it could be the craziest wild, wild west ever. So how do you verify that it's done? Who knows more about exposure and calibration and instrumentation and exposure than CIHs? It just isn't. And I guess the point is if it does or does not happen, I think the effort should be made. And then the education of these different people that are looking at these devices and the programs, educate them, right? And whether it gets mandated or not. But I think you got to make people aware of how critical it is that this thing is handled, not just throw something on the wall and we're done. It just doesn't work that way. It's not going to work that way going forward.
Okay, thanks, Ron. Next question, what are the accuracy claims involved and how do other IAQ monitors handle this?
So every instrument on planet Earth, if you look at the specifications, it'll give you a plus or minus tolerance. It will give you the temperature range, the operating humidity range, and all that is included. And very often there's a stipulation that says, hey, that's why you calibrate every time before you go in, or check calibration before you go into a confined space or whatever, because nobody knows what happened to those sensors in the interim. So a lot of claims that get made really are done based on competition, not based on the reality of the instrument. So, you need to make a good claim that makes sense. So if you're not calibrating and you're not checking, how can you ever even get close to the claim? Our claim was plus or minus 20% of reading across the range. And now as we've gone through calibration and we see the accuracy of these devices, we'll tighten that up. And part of the reason for us to tighten it up is the research bodies that want to use this data to start correlating other things to the data. And if the data is inaccurate, it's not going to be useful. So that's the reason the universities are involved and why we're working with BPS and the universities to attain the best data we can and tighten that band up to plus or minus 10, or maybe even in some cases plus or minus 5. But will we do that without validating? We won't do that. But we're seeing really good data at this point.
Okay, Ron, the next question is from Alan, who asks, how many monitors per school are installed to ensure that you get good representative samples?
So in the case of the particular school district we're talking about, we're working with several other at this point, but the key was equity. And the biggest, if you think about exposure, right, the biggest exposure is places where people accumulate in a room and could or could not have ventilation or adequate ventilation or filtration. So Boston Public Schools elected to put one in every classroom, every main office, and every nurse's office. And then we have them on the roofs. So every single classroom. So for example, some of their bigger high schools, we have one high school that has over 350 units in it. Then we have smaller schools that have 12. But it's every single classroom, every main office, every nurse's office.
Okay, Robert asks, was there any field calibration done in addition to the annual lab cal?
So the units, the initial, when we put them together in East Syracuse, we did the assembly, we did calibration in Syracuse. They were installed in the field and we checked calibration at the outset. During that process, we have all that data and what the readings were. And again, we were using plus or minus 20% for fail or pass. And we have all that data. Part of the issue that we ran into was the speed that we were installing and the ability to verify calibration and do any modification upon installation. That's the reason for the first year, we're actually going back and looking at that data, and trying to determine if we can do a back calculation to see the data correction or how bad was the data. And we're in the middle of that right now. All that's being done. What's interesting is because we record the actual output of the sensors prior to any calibration factors, we can now back calculate using the actual sensor parameters. And so it's a really interesting exercise. And when we get it done, it'll be available to the public. And I would say, it's probably another month or two out from getting it all done because there's, 12 terabytes of data that are being processed. So it's going to be a big process, but it's all being done as we speak.
Okay, thanks, Ron. Luis asks, is there a way to check or verify sensor monitor accuracy from a third source, such as a vendor?
So if we're talking about the claim put in a specification, there are some third-party tests that take place on some of this. There's different associations around the world that do this. But again, when a manufacturer sends them typically to those people to test them, these are handheld units. They're babied and they're taken care of. And so there could be some inaccuracies. When we first looked at a lot of these instruments, we did our own study in-house within SGS Galston. We actually bought every available instrument and tested them in a chamber using certified test gas, using reference instruments. and we determine which ones are good, which ones are bad. We like what we're doing now because we're using industrial grade sensors. These are sensors that are in industrial grade products, and we just have a lot of faith in them, and we've got a lot of experience with them. Not to say that we're not going to move towards some semiconductor-based sensors as we go forward, but we'll only do that as we confirm their performance. But we'll never ever do without calibration, or we will never ever do anything quote automated calibration, or it calibrates itself. We'll never touch a device that does that.
Okay, thanks, Ron. It looks like we may have come to the end of the questions. We'll give everyone another minute or two in case another one rolls in. I'll answer a question that I often get for Synergist webinars, and just want everyone to know that we will update your educational transcripts to reflect your attendance at today's webinar. That update process has a manual component and can take a few weeks to complete, and all attendees will receive an email when their transcript is updated. And we do have a couple more questions come rolling in from Robert. He asked, what was the biggest surprise for you about this endeavor?
I'll tell you, so whenever you, when we first started down the path of this calibration effort, so naturally, if you set your reference CO2 level at a concentration, call it 450, and the technicians inadvertently had gotten close to the instrument and interfered with basically the readings of the SmartSense unit, the unit would read high. So the unit might go to 550, 600. But in the calibration process, they put in 450. And what we saw at a very early stage is we would monitor the classrooms as they were calibrated, and at night, we would see the level drop to 300. Well, anything below 400 becomes a little bit suspect, right? So we started trying to figure out why it was dropping below 400. Well, it's because that technician getting close and applying everything to the instrument prior to getting the reference levels properly set caused the instrument to read high, and so that he would set his first point of calibration too high. And so when the unit would go down at night and nobody's around, we would see it go into a range that is basically atmospherically impossible. And so we very quickly corrected how they were doing that. And you don't think about those things. And keep in mind, we're trying to be within 50 ppm or whatever. And man, just it doesn't take much, right? You exhale, I think it's 30, 40,000 ppm of CO2. So it doesn't take much CO2 if you're within a range of a device to cause it to read 10 or 20 or 50. And that was the thing that was very interesting. You know, when you get into these situations and you've calibrated a million instruments, and then you look at them and go, what is going on? And then, there's always a rhyme and a reason for why things occur, and that was what the reason was. That was my biggest, after years of doing this kind of stuff, that was what really shocked me. And we just corrected the process. So, good question.
All right, thanks, John. Unfortunately, that's all the time we have for today. If we didn't get to ask your question, we'll be sharing that with SGS Golf and with Ron, so please know that we'll pass that along. My thanks to Ron Mcmahon for his presentation, to SGS Carlson for sponsoring today's webinar, and to all of our participants. Our next Synergist webinar, Autotoxicants, Identifying a Missing Link in Hearing Loss, will be held October 25th at 2 p.m. Eastern. You can register at aiha.webvent.tv. Have a great day.
Thank you very much. Take care, everyone.
Thank you, everyone. This actually concludes today's webcast. Thank you all for attending. The recording will be available at aiha.webvent.tv. We will send all registrants an email tomorrow with that link. And please visit our event calendar to sign up for future webcasts.